Data was collected on the height and corresponding weight of 5 randomly chosen professional women swimmers. Just glancing at the chart, it appears that the taller the woman swimmer is, the heavier they are. So that makes sense based on our experience. I do think that there probably is a relationship between height and weight. We'll be able to measure that statistically later to see how significant that relationship is. But for now, we're asked to graph the data and get a visual of how these variables are related, and also to create the line of best fit, or the equation of the line of best fit. We want to use the height of a woman swimmer to help predict her weight. So that will set up our variables. X will be the height and Y will be the weight. Remember, in algebra, X was the independent variable and Y was the dependent variable. So when you created a formula or a linear function or equation for the relationship between X and Y, X is the value that you put into, and then Y was the value you calculated back. Y depends upon what value you put in for X. The most important thing is that we recognize here that we're going to use height to help us predict a woman swimmer's weight. So let me go ahead and start to construct a graph. Notice that both the height and weight values are positive. So we're basically in quadrant 1. We're going to call height our X variable, and our Y variable is weight. Now the X variable has values 68, 64, 62, 65, and 66. So 62 is the smallest, 68 is the largest. So I might break the axis here and start at 62, 63, and just go by one. 64, 65, 66, 67, and 68. The weight variable, 132, 108, 102, 115, and 128, the smallest value there is 102, and the largest is 132. I could also break that one, but I'm gonna start and just make my unit measure 20. 20, 40, 60, 80, 100, 120, 140. And now to try to graph these, let's see, I'd have 68, 132. This is a real rough graph. 68, 132 would be about right there maybe. 64, 108, so maybe about right there. 62, 102, 65, 115, and 66, 128. Okay, so I've graphed my data, and from the graph, I can see that as the height of the person increases, there is an increase in weight. Now, we're after a linear model of this data, what's sometimes called a regression line, or a line of best fit, a least squares line. There's several names for that also. But it's basically just a line that averages its way through the data set. It tries to fit as close to all the points at the same time as possible. And we recognize, because there are other variables involved in how much a woman swimmer weighs, not just her height, but there's other variables that would contribute to her weight, and the fact that there's a certain amount of measurement error. We're not expecting all these points to line up, but we're getting sort of an average model of, or generally what the relationship is, in the sense that the line of best fit is sort of an averaging line through that data set. For every height, it will give us an estimate, a rough estimate of where the weight would be. So there's nothing perfect here, but we want that line to fit the data as best it can. And I could actually do this problem if I put this on graph paper and took and was able to control my graphing and be very, very careful and get a ruler and draw the line, I could use some techniques that I learned in algebra. I could find a couple points on the line and use those points to get a slope, and then with one of the points use the point slope form to get an equation. And just with graph paper, a pencil and a ruler, I would be able to get pretty close to this line and get a good formula that would help me get an estimate, a reasonable estimate of a woman swimmer's weight based on her height. But what we're learning in these first couple sections of chapter 11 is how do you do this with formulas or software. So I want to demonstrate that with formulas. Now the formulas are derived from calculus. It's an optimization problem. Calculus helped us to create this line of best fit. The line is as close to all the points at the same time as it could be. It minimizes the total sum of differences between the points in the line. And if you follow these formulas, that's what you'll get. Excel can do that for us, but let's go ahead and see how the formulas work. So my formula for this line, I'm going to write, and these are the symbols used, y hat equals beta sub 0 hat plus beta sub 1 hat x. Now, the beta sub 0 is basically, if you remember from algebra class, we would have said y equals mx plus b, or writing it in the order that we're seeing here in the textbook, it would be this order. Our y-intercept is the beta sub 0 hat, and our slope is the beta sub 1 hat. So again, this is pretty much just algebra. All we really need is the slope and the y-intercept. We need the beta sub 1 hat and the beta sub 0. So let's start with the beta sub 1 and look at the formula. And then the beta sub 0 can be calculated from that. To do this, it appears that I'm going to need x bar and y bar, and then I'm going to have to subtract those values from each of the data points, the x coordinate and the y coordinate. And then it looks like I need to square that difference between the x coordinate and the x bar and add those up for the denominator. Probably the best way to navigate through all this is to set up a table. Anytime you have a summation, you've got to do several of repeated calculations. I'm going to put my x sub I, and again, x represents the height variable. So that would be 68, 64, 62, 65, 66. And then my corresponding y coordinates, 132, 108, 102, 115, and 128. So let's calculate an x bar, and let's calculate a y bar. The x bar is the average of the x coordinates of my collected data. So my x bar would be 325 divided by 5, which would be equal to 65. My y bar would be 585 divided by 5, which would be 117. So if I calculate my x sub I minus x bar values, I'll get 68 subtract 65 would be 3. 64 subtract 65 would be negative 1. 62 subtract 65 would be a negative 3. 65 subtract 65 would be 0. And 66 subtract 65 would be 1. Next, I'm going to go ahead and get my x sub I minus x bar squared. And so that would be 9, 1, 9, 0, and 1. Next, I'm going to get my y sub I minus y bar. So 132 subtract 117. is 15. 108 subtract 117 is minus 9. 102 subtract 117 is minus 15. 115 subtract 117 is minus 2. 128 subtract 117 is 11. Okay, I need to take the x sub I minus x bar and multiply it by the y sub I minus y bar. This part right here is going to help me calculate the numerator. Once I get these values, all I have to do is just add them up. So that would be 3 times 15. So my first one would be 45. I would have negative 1 times negative 9, which is 9. Negative 3 times a negative 15, which again would be 45. 0 times negative 2 would be 0. 1 times 11 would be 11. So if I add those together, that will be my numerator for my slope. So the sum of the x sub I minus x bar, y sub I minus y bar, is equal to 45 and 45 is 90. 90 and 9 is 99. 100, 110. So my value for the numerator for my slope is 110. Now my denominator would be this value here, but add it. So if I add the x sub I minus x bar squareds, then I have 9 plus 1 is 10, and then 9, 19, and 1, so that would be a total of 20. So my slope would be equal to 110 over 20, which would be 5.5. And then using my formula for the beta sub 0 hat, y bar minus beta sub 1 hat x times x bar. So beta sub 0 hat would be equal to 117 minus 5.5 times 65. And that calculates out to minus 240.5. So my formula would be y hat is equal to minus 240.5 plus 5.5x. And that is the equation or formula for this line of best fit.